Hey guys, welcome back to Genius Learning. Okay, so in part 4 of our projectile motion, I want to show examples now and how to use the vector equation that we've been using. So the first one is going to be our displacement vector equal to the initial velocity vector times time plus 1/2 a vector t squared. Okay, so this is our vector equation, which looks like this type of triangle, right? We got a vector displacement pointing to our final position. We got initial velocity times time vector, and the one going down is going to be 1/2, and I'm going to put g t squared. So we just start getting used to writing g as our vector going down, because that's always going to be the case. So acceleration in the x is going to be 0, and acceleration in the y is going to be gravity. Okay, so this general notation is because we have a displacement in the x, and we also have a displacement in the y, which I explained in previous videos. But the acceleration in the x is always going to be 0, and the acceleration in the y is always going to be g. So when we do the triangle like this is always going to be g. Okay, so just write the vector because it's going downward. All right, so with this vector equation, I want to do 3 examples, and then with the new vector equation that we looked at last video, I want to do 1 example. So velocity final is going to equal velocity initial vector plus a vector t. Okay, and again, this vector triangle looks exactly like the other one, and so we can actually draw it not at the origin if we don't want to. So we're gonna do velocity initial goes here, velocity final, and downward is gonna be our gravity times time. So again, we're gonna change the notation of a to g when we're talking about going in the y direction. So this also has 2 velocity finals: velocity final in the x and velocity final in the y. Okay, and in the previous videos I also explained these 2, and now we're going to work some examples to see a little more about how we can use them. Okay, so in the first example, let's look at a projectile motion problem where we throw, let's say, a baseball. We throw a baseball, and this is the trajectory, okay, and this is the x final, okay, which is 40 meters away. Okay, our initial velocity is unknown, so we don't know our initial velocity, but we do know the angle that it was thrown, which is 30 degrees. And we know that the time that it landed here is going to be t final equals 4 seconds. Okay, so that's all the information that we're given. We're given that the angle that we throw it at is 30 degrees, when it lands is 4 seconds, and it was 40 meters away. Okay, these are things that we can calculate kind of just by looking. You know, we know how far something went. We could put in our stopwatch 4 seconds, and then we can, you know, sort of roughly measure the angle. And with those, we can actually calculate the initial velocity that it needed to be launched at in order to meet 40 meters at 4 seconds. Okay, so let's use our displacement equation, and let's draw the triangle onto our projectile motion picture, always. And so we're gonna do the displacement vector always goes to the position final. So we're gonna draw a vector from here to our final position, always. That's the first thing that we do. We're gonna label that D vector. Okay, so the first thing we do, point a vector all the way to the final position. Then we're gonna point the next vector, velocity initial times time, in the direction where initial velocity is going, all the way until we have a vertical line here. So we'll stop right there. So we're drawing a vector here that represents V naught t, right? So that's this term in our vector equation. And then now we need the last term. Okay, and the last term, 1/2 gt squared, gravity, is always pointing down. Okay, always. Gravity always points down. So this vector always needs to be pointing in that direction. Okay, so that's 1/2 gt squared. Okay, so now, whoa. All right, now we have our vector triangle. Okay, we have a 90-degree triangle, which is good because now we can use trig in order to solve this problem and make it easier for ourselves. So let's try sine theta is gonna equal, so sine of this angle is gonna equal the opposite, right? This entire side, which is 1/2 gt squared over hypotenuse, which is this entire side here, which is V naught t. Okay, I can cancel out one of the t's, and we're looking for initial velocity. So if I move this initial velocity here and sine theta down here, we get V initial is equal to 1/2 gt over sine of theta. And if you notice, we have all the values on this side of the equation. We know gravity, we know the time where it where it landed, and we know the angle that it was shot at. So it's gonna be 1/2 9.8 4 seconds over the sine of 30. Okay, and that should give you your initial velocity. All right, I don't want to calculate things. You guys can calculate that on your own, but I want to show you the concept of how to find these things. Okay, let's move on to the second example. All right, so for the second example, we have, let's see, we have a projectile being launched at an initial velocity of 5 meters per second. Okay, so it flies, it lands here, and it lands there at t final equals 3 seconds. Okay, this is 40 meters away. So here is x final, and this is where it originated from. Okay, at an angle that we don't know. Okay, so in this problem, we don't know the angle. So here we didn't know velocity initial, here we don't know the angle. But we do know the distance it traveled in the horizontal up to our final position, the time final that it took, and the velocity initial. So let's draw our vector triangle, okay? What do? We're gonna draw our displacement vector to our final position, always. So final position, vector goes first, okay? Then we're gonna draw our V initial times time. So we're gonna draw this vector, okay? And that's V initial times time. And our last vector is going to be our gravity vector, which goes down. Okay, always goes down. This vector always vertically downward. 1/2 gt squared. All right, so once we've drawn our triangle and we make sure that this is a 90-degree angle, then we can use our trig identities. And so we need this angle, okay? We know this side because we know the time final, and we know gravity is 9.8, and we know the bottom. So I would try to go with tangent theta. Tangent theta is opposite over adjacent, okay? And if we solve for theta, we're gonna have the inverse tangent of 1/2. This is 9.8. The time is 3 seconds squared, and underneath that we have 40. Okay, so we have all the values inside of our tangent inverse, and with that we find the angle that it was launched at. Okay, so ran out of room here, so I know I said 3, but I'll do it in the next video. Let's start with this vector equation for final velocity and see how we can extract information using that. So let's look at a similar system, projectile motion. This time, let's throw a football. All right, spinning, and it follows this type of trajectory. This is the x direction, and it falls right there. This is our x final. Okay, it is, the angle here is unknown. Okay, our velocity initial is unknown. The only thing that's given to us is that in the x direction, so velocity initial in the x was equal to 20 meters per second, and the velocity initial in the y was equal to 16 meters per second. Okay, so that's the only information given to us, and it may seem like nothing, but just with these two pieces of information, we can find the angle that it was launched at, we can find the time of max height, we can find the final time, we could find initial velocity, we can find a couple other things, a displacement in the x. Okay, so let's just look at a couple things we can find. So we have our projectile motion picture, right? And just like these problems, we have to draw the triangle of our displacement vector on top of this system. So let's do that. All right, so I want to draw this velocity final vector equation up here, and up here is exactly in the middle, so this is max height. So the reason that I'm going to draw this vector equation at max height is because I want to take advantage of the fact that v final in the y is equal to 0, okay, at max height. So you need to remember this. At the maximum height of your projectile, the velocity in the y direction is 0, all right, because that's the highest it's going to go. After that, once you move towards the right, it's going to start to go down. The velocity in the x final is not 0. It's still moving towards the right. Okay, so only the velocity in the y is equal to 0 at max height, not for the x. So let's do this vector, which represents our velocity final in the y. Our initial velocity, right, has to be drawn the same, and so we have initial velocity in the y, right? And then we have gt. So this vector right here always points down for the y, okay? For the x, it's 0. So this is gt. So these are all vectors, okay? So now that we've drawn our triangle, we see that we have a right triangle, and this angle is the same as this angle here, okay? So now let's use that triangle, and let's use the fact that at max height, velocity in the y is equal to 0. So this equation for the y is velocity final in the y is equal to velocity initial in the y minus gt, is a gravity, okay? So having this equation here and knowing that at max height where we drew our vector triangle, if velocity final in the y is 0, now we have this relationship here, and you remember what velocity initial in the y is. So this is velocity initial in the y, and luckily in this problem it's already given to us as a value. So let's solve for time. So time is going to be equal to v initial in the y over g, which is equal to 16 over 9.8. All right, and so t max height is equal to 1.63 seconds. This is at max height. So remember what I told you in the previous video, that at max height, which is here, okay, t is equal to 1.63. Now, if we just double it up, then we have the final time here as t is equal to 2 times 1.63, because it follows a parabolic trajectory. So this side is equal to this side, okay? So, but for now, let's just leave it at max height, but that's also something you're gonna also need to identify when you find when you find the time at max height. Remember that if you just multiply it by 2, you can get the final time, and then you can further solve for things that you need. Okay, so now once we have the max height, right, I want to find out what my initial velocity is, right? What is my initial velocity? Well, we got an initial velocity in the x, and we got an initial velocity in the y. So if you remember from the previous videos, our magnitude, right, which explains our distance from the origin, or this distance from the initial to the terminal, is equal to velocity initial in the x squared plus velocity initial in the y squared. And that means that this notation has to be velocity initial, because that's what we're interested in. Okay, so knowing that, we have these two values, right? We have y equals 16 and v of the x is 20. So we have here square root of 20 squared plus 16 squared, which gives us initial velocity of 25.6 meters per second. Okay, so we found initial velocity and we found the time at max height. All right, and so now let's solve for the angle. So again, using our vector triangle, right? Let's draw it right here. We got v initial in the y vector. We got v final in the y. And we have our vector that goes down, which is always gravity. Okay, we make sure that it's a right triangle. And now we know our velocity initial in the y because that was given to us. We found our time of max height, which is where we put this triangle. Okay, we know gravity, and velocity final, we don't need it if we think cleverly. So by cleverly, I mean, let's choose trig identity. Let's choose sine theta, okay? Sine theta is gonna be opposite, right, over hypotenuse. And so I know all these values here, right? I have gravity, I know the time, and I know the velocity initial, right? You don't want to choose tangent because tangent means that you're going to have opposite over adjacent. Okay, so let me show you here. You don't want to choose tangent, which is going to give you opposite over adjacent, because you don't know velocity final in the y, and you don't know the angle, because that's what we're trying to find. So this equation won't be no good for you. Also cosine. You don't want to choose cosine because cosine is adjacent over hypotenuse. We don't know the adjacent and we don't know the angle, so that's two unknowns. So we're being clever by choosing sine, where we know the opposite value and we know the hypotenuse value. Okay, so if I solve for theta, we're going to have theta is equal to the inverse sine of gt, so 9.8 times the time and max height, right? Because we're here with this vector equation, all right, over velocity initial in the y, which was given to us initially, so that's 16. And so with this, we can calculate the angle that it was launched at. Okay, so just to recap here, we're looking at this displacement vector equation, right? This is the triangle associated with it, and we have our velocity final vector equation, and this is our triangle associated with it. And so we're solving for different things inside of the projectile motion problem, right? You have to draw the triangles and then see what you can solve for. See if you can just do trig identities like sine and tangent, or in the case of this problem here, we have to think about the velocity in the y at maximum height is 0. And so if we use this equation, given the initial values that were given to us, we can work out the things that we need in a different way. For example, here we have 0, which allowed us to solve this equation initially for time at max height. All right. Here, knowing that the magnitude is equal to the square root of the velocity initial in the x squared plus the velocity initial in the y squared. So we were able to find the velocity initial. And knowing those two things, now we have our triangle again, and we use sine theta because we know the values of this side now, we know the values of the hypotenuse, and that allows us to solve for theta. Okay, so in the next couple problems, I'll be going in more depth. We can find the height. So we can find this actual height right here. So what is the height at the maximum height? You know, we have the time at max height. We know that velocity y is equal to 0 at max height. What is that height? Okay, so we can solve for things like that. We can also solve for things like how far did it go? What is the displacement in the x? And a couple more things. So let's understand this first, because now we're gonna look at more and more complex problems for projectile motion, okay?